seeds of life discovered in young stars' planet-forming disk. Imagine this. The very seeds of life hidden within the swirling disks of gas and dust around a young star may hold the answers to one of humanity's biggest questions. How did life begin? A groundbreaking discovery by astronomers has revealed that complex organic molecules, often considered the precursors to sugars and amino acids, can be found in the planet-forming disk of a distant star. This revelation not only deepens our understanding of the universe, but also raises intriguing possibilities about how life might emerge elsewhere. But here's where it gets controversial. Are these findings just a glimpse into Earth's past, or do they hint at a cosmos teeming with untapped potential for life? Using the awe-inspiring capabilities of the Atacama Large Millimeter, submillimeter array, ALMA, a team of researchers led by Abubakar Fadul from the Max Planck Institute for Astronomy, MPIA, made an extraordinary leap forward. They identified a staggering variety of complex organic molecules within the protoplanetary disk encircling V883 Orionis, a young, outbursting protostar located in the constellation Orion. Among the 17 distinct compounds detected were ethylene glycol and glycolonitrile, both observed for the first time in such an environment. These molecules are believed to act as early chemical building blocks that could eventually lead to the formation of life. This discovery adds another layer to the growing body of evidence, suggesting that the ingredients necessary for life don't originate exclusively on planets like Earth. They actually begin their journey in the vastness of space. By comparing different cosmic regions, scientists have noticed a clear trend. As systems evolve from primordial star-forming clouds into fully mature planetary systems, the concentration and diversity of complex molecules increase significantly. This pattern strongly supports the theory that the raw materials essential for life are commonly produced in space and distributed widely throughout the universe. The team's findings were published in the astrophysical journal Letters, marking a pivotal moment in astrochemistry. Previously, astronomers had already uncovered complex organic molecules, COMs, in areas associated with star and planet formation. These COMs typically consist of more than 5 atoms, including at least 1 carbon atom, and often represent the precursors to life-supporting chemicals, such as amino acids and nucleic acids. However, the detection of 17 unique COMs in V883 Orionis provides unprecedented insight into the evolutionary process of these compounds. For instance, glycolonitrile stands out due to its role as a precursor to glycine and alanine, both crucial amino acids, and adenine, a key component of DNA. Could this mean that the path to life is more universal than we ever imagined? The synthesis of prebiotic molecules begins in interstellar space, long before stars and planets take shape. As Abubakar Fadul explains, our finding points to a direct line of chemical enrichment and increasing complexity between interstellar clouds and fully evolved planetary systems. Yet this journey isn't without challenges. When a cold protostar transitions into a young star surrounded by a disk of dust and gas, it undergoes violent phases characterized by shock waves, intense radiation, and rapid gas ejections. Such energetic events were once thought to obliterate much of the complex chemistry formed during earlier stages, leading scientists to propose what was known as the reset scenario. According to this hypothesis, most of the chemical compounds needed for life would need to be recreated within circumstellar disks during the formation of comets, asteroids, and planets. However, the latest research suggests otherwise. Now, it appears the opposite is true, notes Camber Schwartz, an MPIA scientist and co-author of the study. Their results indicate that protoplanetary disks inherit complex molecules from earlier stages, and the formation of new ones can continue during this phase. In fact, the brief period between the energetic protostellar phase and the establishment of a stable protoplanetary disk wouldn't allow enough time for detectable amounts of comets to form if they weren't inherited. This implies that the conditions setting the stage for biological processes might be far more widespread across the universe than previously assumed. To better understand this phenomenon, consider the simplest organic molecules, such as methanol, which have been spotted in dense clouds of dust and gas predating the birth of stars. Under certain conditions, these environments can even host more intricate compounds, like ethylene glycol, one of the species recently identified in V883 Orionis. Tushar Suhasaria, head of MPIA's Origins of Life Lab and a co-author of the study, elaborates. We recently discovered that ethylene glycol could form through UV irradiation of ethanolamine, a molecule recently found in space. This finding reinforces the idea that ethylene glycol could emerge in these environments, not just early on, but also during later stages of molecular evolution when UV radiation plays a dominant role. As we zoom out to examine the broader picture, it becomes evident that the agents critical to biology, amino acids, sugars, and nucleobases that make up DNA and RNA, are present in asteroids, meteorites, and comets scattered throughout our solar system. But how do we access these hidden treasures? Many of these complex molecules reside buried in ice, shielded from view, until external forces bring them to light. In icy realms, chemical reactions occur under frigid conditions, ideally on frozen dust grains that eventually clump together to form larger celestial bodies. Trapped in mixtures of rock, dust, and ice, these molecules usually remain undetected unless probed directly by spacecraft or exposed through external heating. Within our solar system, the sun acts as a natural furnace, warming comets and causing them to release impressive tails of gas and dust, or comas, which are essentially gaseous envelopes surrounding the comet's nucleus. Spectroscopy, the technique of breaking down light into its constituent colors, allows astronomers to identify the spectral fingerprints of these liberated molecules, offering clues about their composition. A similar heating mechanism is at play in the V883 Orionis system. The central star continues to grow by pulling in gas from its surrounding disk, gradually approaching the point where nuclear fusion will ignite in its core. During these growth spurts, the incoming gas heats up, triggering powerful bursts of radiation. These outbursts are strong enough to warm the surrounding disk, releasing the chemicals we've detected, Fadul explains. Complex molecules, including ethylene glycol and glycolonitrile, emit signals at radio frequencies, making ALMA the perfect tool for detecting them. Operated by the European Southern Observatory, ESO, ALMA sits high in Chile's Atacama Desert at an elevation of 5,000 meters, granting astronomers the precision needed to pinpoint faint spectral signatures in the V883 Orionis system. Despite the excitement surrounding this discovery, the story doesn't end here. While this result is thrilling, we haven't yet unraveled all the spectral signatures we've encountered, Schwartz admits. Higher resolution data will help confirm the presence of ethylene glycol and glycolonitrile, and might even reveal additional complex chemicals we haven't identified yet. Fadul adds, perhaps we need to explore other parts of the electromagnetic spectrum to uncover even more advanced molecules. Who knows what else lies waiting to be discovered? And this is the part most people miss. While the scientific community celebrates this milestone, it also invites us to ponder bigger questions. Are we truly alone in the universe? Or does the cosmos brim with countless opportunities for life to arise? Share your thoughts in the comments below. Do you think these findings reshape our understanding of life's origins? Or is there still more to uncover? Life's building blocks found around baby star, implications for extraterrestrial life. Imagine if the essential ingredients for life were not as rare in the cosmos as we once believed. A groundbreaking study suggests that the building blocks of life might be far more abundant in space than previously thought. This revelation comes after astronomers discovered key components of life's building blocks orbiting a distant young star, V883 Orionis, located approximately 1,300 light-years away in the constellation Orion. The material found swirling around this protostar includes 17 complex organic molecules such as ethylene glycol and glycolonitrile. These molecules are precursors to essential components found in DNA and RNA, the very blueprints of life. This discovery, published in the Astrophysical Journal Letters, challenges our understanding of how common the chemical precursors to life really are. Previously, scientists believed that the violent processes involved in star formation would destroy many of these compounds, leaving life seeds scattered only in rare planetary systems, capable of reproducing them. But here's where it gets controversial. The new findings suggest the opposite. The study indicates that protoplanetary disks inherit complex molecules from earlier stages, and the formation of these molecules can continue during the protoplanetary disk stage. This means that the ingredients for life might be more resilient and widespread than we ever imagined. For decades, scientists have been tracing the fundamental chemicals necessary for life's origins across the universe. This search has uncovered prebiotic molecules in comets, asteroids, and even floating in the gas and dust of interstellar space. Stars begin their lives in clouds of gas and dust, which gradually collapse and heat up as they form protostars and protoplanetary disks. From these disks, comets, asteroids, and planets eventually emerge. However, this process is incredibly violent, with outflows of shocked gas and intense stellar radiation, producing enough energy to disrupt and even reset the steady chemical enrichment that leads to complex organic molecules. Using the Atacama Large Millimeter / submillimeter Array ALMA, a collection of 66 radio telescopes in northern Chile, the researchers behind the new study detected emission lines from a cluster of organic molecules within V883 Orionis's protoplanetary disk. The young star is still undergoing nuclear fusion at its core, leading to powerful bursts of radiation. And this is the part most people miss. These outbursts are strong enough to heat the surrounding disk, even in icy environments, releasing the chemicals that the scientists detected. This discovery suggests that instead of destroying these organic compounds, the star's growth could be freeing them from the icy surfaces upon which they typically form. This points to a continuous line of chemical enrichment and increasing complexity between interstellar clouds and fully evolved planetary systems. While the results are thrilling, the scientists caution that they remain tentative. They need higher resolution data to confirm their detections and conduct closer studies of how well these compounds hold up as their host star grows. Perhaps we also. Complex organic molecules found in planet-forming disk, clues to life beyond Earth. What if the ingredients for life are scattered across the cosmos like cosmic confetti? A groundbreaking discovery might just rewrite our understanding of how life's building blocks form in the universe. Astronomers have uncovered evidence of complex organic molecules, key precursors to life as we know it, in a swirling disk of gas and dust around a young star, 1,305 light-years away. This finding suggests that the chemical foundations of life might not be exclusive to Earth, but could be forged in the vast icy nurseries of stars and delivered to planets still in the cradle of formation. But here's where it gets controversial. This challenges long-held theories about when and where these molecules can survive. Let's dive deeper. Using the Atacama Large Millimeter submillimeter Array and ALMA in Chile, scientists detected 17 complex organic compounds in the protoplanetary disk of V883 Orionis, a star estimated to be just 500,000 years old. For context, our Sun is 4.6 billion years old, so V883 Orionis is a mere toddler in cosmic terms. This star is in the chaotic phase of gobbling up material from its surroundings to grow, while simultaneously birthing planets in the dusty donut-shaped disk encircling it. The molecules found here include ethylene glycol and glycolonitrile, which are stepping stones to amino acids like glycine and alanine, as well as adenine, a cornerstone of DNA and RNA. And this is the part most people miss. These compounds were previously thought to form only in the later stages of a planetary system's life cycle, not during the violent early years of a star's adolescence. The discovery flips the script on a theory known as the reset scenario, which posits that life's essential chemicals can't survive the tumultuous conditions of a young star's environment. Instead, new data shows that complex molecules might actually persist and even thrive during this chaotic phase. Camber Schwartz, a researcher at the Max Planck Institute for Astronomy, explains our results suggest that protoplanetary disks inherit complex molecules from earlier stages, and the formation of complex molecules can continue during the protoplanetary disk stage. This implies that the chemical pathways leading to life might be far more robust and widespread than we ever imagined. So how do these molecules endure the heat and radiation of a star's violent youth? The answer might lie in icy dust particles. Complex reactions occur more readily in cold environments, so these molecules could be hiding in frozen grains that later clump together to form comets, asteroids, or planets. When a young star's outbursts, triggered by material falling onto it, heat these icy regions, the chemicals are released. This process mirrors what we see in our own solar system when comets from the distant Kuiper belt or Oort cloud swing close to the sun and develop glowing halos called comas. In V883 Orionis's case, the star hasn't yet begun nuclear fusion, but its bursts of radiation are enough to mimic this thawing effect. The implications are staggering. If these molecules can form and survive in such extreme conditions, the chemical seeds of life might be common throughout the galaxy. Abubakar Fadul, lead author of the study, adds a tantalizing twist. Who knows what else we might discover? Future research using different wavelengths of light could reveal even more complex chemicals lurking in these disks. But here's a question to ponder. Could this mean our understanding of life's origins needs a complete overhaul? Are we underestimating how easily life's ingredients spread across the cosmos? Share your thoughts in the comments. Do you think this discovery makes the universe feel more like a cradle of life? Or are we still missing the bigger picture?